Let us move to the last but not the least important part of the transport layer, and it is a congestion control, specifically TCP congestion control. I already hinted a couple of times that if you put too many packets into the network, if you start pumping the network with packets, you not necessarily will have just a cap of the performance. So this would be the case when you just have one directional packet flow, but not the case when you have a bidirectional flow. Like you have sending packets and you waiting for the acknowledgement. If you didn't get the acknowledgement, you send in more packets, and you send in more packets, and you send in more packets. So as a result, you can actually have so-called a congestion collapse. Congestion in general has two costs. One is you reduce the effective throughput. So from the perspective of the guy who is sending data, or the guy who is receiving the data, we're able to send less kind of good put, like less amount of data that is actually kind of new data, the application data being sent out through. And the second part is kind of equivalent, but from the network perspective, we are losing a lot of resources. It's we effectively wasting resources on retransmitted packets and so forth. In general, there are two basic approaches for the congestion control. One of them is related to the network itself giving some information to applications or end hosts that they should slow down. So this one is effectively the ideal way, because the network is the place where the congestion is happening, and applications can effectively react extremely precise and kind of do all what is necessary to do. However, there is a problem. And the problem is that all routers in the world have to understand this common ground. So we have to effectively would have to introduce some common standard. All routers have to obey this standard. And if we invent some new technology, how to deal with congestion a little bit better, it would be impossible to accomplish. So what we actually do in the TCP world primarily is we use so-called end-to-end congestion control. And with end-to-end congestion control, we technically not relying on any signal from the network to give us kind of information about congestion, but rather as an end host, as a sender, we estimate how much we can send. And there are a few signals that we can actually infer from the network by just observing the packets that we're receiving or packets we're not receiving, and do some actions from that. So in the previous lecture, I already mentioned the error recovery part. So there are timeouts, there is this duplicate acknowledgement or fast retransmit. So just using these two signals, you can actually have a pretty good understanding whether you have congestion or you don't have congestion. There's actually one more mechanism that you can use, like RTT measurement, and the changes in RTT value would indicate some form of a buffering happening in the networking or reducing buffering in the networking. And technically, you can have some combination of both network-assisted and end-to-host assisted congestion control, and there are actually implementations that do both. There is a long history of TCP. So this one is just the beginning. It's just very, very beginning. When TCP was initially designed, people actually wasn't aware of the congestion. So they just introduced the standard, introduced all that I have been talking last time, kind of what about the flow control, about basic error recovery, and that was it. So people thought that would be enough, we're gonna transmit packets and everything will be fine. But that wasn't the case. So eventually, kind of when people start actually using TCP and people actually start using this ARPA network, they experienced a very strange problem. And that very strange problem was effectively the congestion collapse. So they seem to have enough bandwidth available for everybody, yet nobody was able to send data to anybody. So as a result, there was in 87 and 88, Van Jacobson actually fixed the problem by introducing the concept of congestion control. And he did it as part of the end-to-end congestion control. And the first approach was very, very basic, very rudimentary, and gave the name Tahoe. That solves the problem, kind of reduced efficiency of the whole process, but the problem was solved. And all subsequent implementation of the congestion control that I'll be talking about are basically building up on top of those Tahoe kind of model, rather improving how fast things have been recovered if error is happening. as I said, the history is long, and this one is just a few notes about this historical timeline of different end-to-end congestion controls that have been implemented over the years. So as you can see, there's like a very initial stuff. There's in 88, in 90, there's something in 92, in 96. There is some some inventions, but then there's around 2004 there was explosion of different suggestions of how we're going to do congestion control. And most of those solutions that were proposed around those years are effectively based on the fact that we need to support fast networks. And most of them are effectively about that. Some of them about long delay networks like satellite networks, because there are some different properties, like there's a long delay, and if you have a very kind of long reaction, you are actually in very, very disadvantaged of that. But the history didn't stop at those times. So there's actually very recent development from Van Jacobson again in 2017. He, as part of the Google team, proposed this BBR. So this is one of the hot congestion controls in modern days. So what is the congestion control? So I hope you remember from the last time I have introduced the concept of the window. So the window, there was a flow control window and there was a receiver window. And flow control effectively define how many packets I can send out without having them to be acknowledged, and there was some relationship with the kind of space of the sequence numbers. So that one, just basic idea of the window. And there was a receiver window, just limit the whole amount of packets that be outstanding based on receiver resources. And what the congestion control, or this congestion control window, or as shown on the website on a slide, is simply CWND, saying that there is yet another limit to define estimated amount of packets that you should send to the network without congesting this network. And kind of everything else is the same. You still have to obey the major flow control window, so your sequence numbers have to be the less, or your window size have to be twice as less than the amount of sequence number that you have. Your actual window has to be less or equal to the receiver window, and again, your window cannot exceed the estimated congestion window. Let me start with the TCP Tahoe. So TCP Tahoe is the congestion control that Van Jacobson designed to solve the ongoing problem. And what it has introduced, the two phases of adjustment of the congestion control window. So one's phase called the slow start, and the other one is congestion control. And there is some form of slow start threshold, like the number that you also dynamically adjust to define which stage you are in at different times. This slide gives details of how the slow start phase of the congestion control is operating. So kind of what slow part is from the slow start is you set the initial congestion control window to 1. You cannot have, as TCP operate on a sequence number that represents bytes, you cannot say 1 packet. So you have to indicate some amount of data. And in TCP terms, they use so-called maximum segment size, or MSS. So this is kind of initialization. So after that, as soon as you have a congestion window set, you now can send the kind of number of packets that correspond to that amount of data. So effectively, you just can send 1 packet initially. If all the packets that you send out and in one batch has been acknowledged, then you increase your congestion window in twice. So if it was 1, you increase to 2. If it was 2, you increase to 4. If it was 4, you increase to 8. If it's 8 to 16, and so forth and so on. So kind of what necessary you need to remember kind of for the left side is all those increases happens on a round trip scale. So you have to send out the batch of interests, batch of packets, and then receive all the acknowledgement, and only that you can increase and send a new batch. You send the batch, receive everything, you increase, you send a bigger batch. So if everything is fine, if your congestion window is still less than a slow start threshold, then you can continue this increase, and continue this increase. I didn't show you on the slide what is the initial value for the slow start threshold, but there is some initial value for that as well, which can be configured in a system, and there are some defaults. And if not all the packets were acknowledged, so if you send out like 64 packets and only a few or like some of them got acknowledged, then the logic for this type of congestion control is simply to set the slow start threshold to the half of that congestion window. So kind of assuming the previous time everything was fine, so meaning that that's a probably good value to have as a congestion window. And then reset congestion window to 1. And then again back to start. And then the process again starting from the scratch, from 1 to 2 to 3 to 4, with exception, so if we reach that the good value that we sent last time, we actually switch to the congestion avoidance system, congestion avoidance phase, which will do slightly different actions. What I'm showing you on the right side is a slightly different way of accomplishing the same thing of the slow start. So instead of clocking on the round trip scale, so instead of sending the batch, waiting for the whole batch to arrive, and then kind of deciding at that point and then sending a new batch, you can actually clock the whole system based on just a single packet. It's slightly kind of, you can try to kind of do some math about this one, but the logic is very simple for the slow start. You simply need to increase, every time you receive the acknowledgement, you have to increase by 1 MSS, so like 1 maximum segment size. The effect for the round trip time would be exactly the same thing. Like if you think about it, if you send out 5 packets, or say 4 packets, you eventually will receive 4 acknowledgements back if everything is fine, and your congestion window will be effectively doubled. So that's the same effect, but you just not you don't have this RTT scale, but rather have the single acknowledgement, and you can send new packets every time. Every time you receive the acknowledgement, you can immediately increase the congestion window. And the rest of the logic is basically the same. If you have some problem or some loss detected, you set the threshold to the previously good value. It will be slightly different from the other approach, but basically will be the same value. You set the congestion window to 1 and you restart the process. As to illustrate, so there's a picture to illustrate the process kind of with the RTT scale. So when I'm sending 1 batch, I'm waiting for 1 packet to arrive. I'm sending batches of 2. I'm waiting for everything to arrive. I'm sending batch of 4 and kind of expecting to receive stuff. There are technically 2 kind of results that you can see for the actual congestion window, or the actual window that is active, depending on what kind of a network limit, depending on what kind of a receiver limit in existence. So for example, if you have a very good capacity of the network, but the receiver is very slow and not eager to process all the data that you're sending, you will see this picture. If you, like over the case A, if your receiver is extremely fast and the network is a little bit slower than the receiver, then what you're going to see, you will see this case B, where a lot of you quickly increase the congestion window and drop into 1. You increasing rapidly, drop into 1. So this would be just a slow start phase. But as I said, there is also congestion avoidance phase, and even Tahoe is doing kind of automatic switching between slow start and congestion avoidance phases. And let me talk about this one. Congestion avoidance, or sometimes called AIMD, or like additive increase multiplicative decrease. And simply the objective is to try to sustain some of the bandwidth. But instead of doing this all rapid increases, rapid decreases, you try to increase slowly just to probe if there's a kind of more resources available. And as soon as you kind of detect that some packets are being lost, then you drop to 1 or to half or to something. So this is effectively what can happen to the network. So if everything is fine, you increase by 1, okay, but in this picture, you increase by 1 within RTT. So for example, if you send out a batch of 5, if all 5 received, you increase by 1. You now send in 6. If all 6 received, you increase by 1, meaning that you start sending 7. And if something bad happens, you half it from 7 to 3 or to 4, depending on how you're averaging. I also included this ACK clocking mechanism, so basically similar to what I was showing on the previous slide for the slow start, but rather different mechanisms. So this one is a bit more complex formula. So instead of just +1, you have to do is +1 squared divided by congestion window. But if you do mathematics, like considering the RTT time, you will see that eventually it will try to increase just by 1 MSS for the RTT batch. To give you just a combined idea of what Tahoe is actually operating, so as you can see, it starts with a slow start phase. It's rapidly increasing up until there's some form of a network limit. Then it's rapidly decreasing, and then restarting from the slow start, and then increasing up to the half of the initial network limit that was detected. And after that stage, it's trying to do slow start. And it's slow, kind of increasing, and then potentially dropping either to half or to 1. I think for the Tahoe, it's not picture that I was showing on the previous slide, but rather it's every time it's detecting all the problems, it's dropping to 1. And then again, restarting from the slow start, switching to the congestion avoidance, and kind of waiting until some kind of loss detected, and dropping to 1 and restarting the whole process. It's maybe not 100% efficient, even in long or short run, but it solved the problem at the time. The famous modification that Van Jacobson himself did very quickly is to simply avoid doing this drastic drop into 1 after the some loss detected during congestion avoidance, and instead of dropping to 1, drop into half of the congestion window. So this is exactly what you see on this picture. So now you have only one slow start phase initially, then you're dropping to whatever, half of it, or to 1, depending on what kind of loss being detected. And you again increasing, you drop into half, increasing, drop into half, and so forth and so on. One thing that I would like to note here, there is actually a difference from TCP perspective. This applies to all TCPs between timeout event and this fast retransmit event. So the timeout is actually really bad kind of event because it indicates that none of the packets that you sent out within last batch has been received, because normally we have only one timeout per batch. Or per unit of time, and this simply indicates there is something really bad happened in the network. So if such a timeout is detected, most of the congestion control will drop to 1 and will restart from the slow start. However, if you detect loss using 3 duplicate acknowledgements, meaning that you received acknowledgement and then 3 duplicate of the same acknowledgement, then it means that something was lost. Look, there's definitely not enough capacity potential. Assuming the loss is only because of the congestion, then you detect that something bad happened, but it's not critical. So in that case, you can kind of think that, oh, we still have traffic in the network going. There is no reason to drop drastically to 1. We can just half of it and try to send out more. Okay, so that's a kind of basic idea of the stages of the congestion control. So remember, there is a slow start, there is a congestion avoidance, slow start starting from slow but very rapidly increasing, congestion avoidance starting kind of starting from the slow start threshold, and then trying to gradually, very slowly increase the congestion window until something bad happens, and then it will try to reduce relatively drastically, and then continue again kind of this slow process of increasing. Now it's an interesting question about the throughput. Let's say we consider this throughput as a kind of in a steady state. When in a steady state in Reno, we have the congestion avoidance. The throughput in the congestion avoidance case will not be even only one TCP flow in existence. It will not be the capacity of the network. And just because we always trying to reach the capacity of the network, and then as soon as we detect the problem, we drop our sending rate. Then we slowly increase our congestion window, like slowly increasing our pipeline up to the network capacity, and then drop into the half, and keep doing that one. so it may not be necessarily the exact formula here, but if you assume the congestion window approximates the good put or throughput for the TCP, then you can get to the formula stating that the actual throughput or potentially theoretical throughput that the TCP Reno can have is actually 3/4 of the maximum throughput of the network. So if your network limit is X, TCP throughput of one flow will be 3/4 of X. So it's it looks a bit bad, but in reality it's not that bad, because we don't really have, usually we don't have just one flow in the network, but rather some combination of multiple flows. And what happens in reality is when you have a mix of TCP flows, then they actually consume all available bandwidth in the network. So now I talked quite a bit of TCP Reno and like all its different stages. Now basic question is, why the heck we have all this explosion of different congestion control algorithms that we developed in the past? And one simple reason, especially the explosion at that period of time, was inability of this basic Reno TCP to utilize all the resources of fast networks. So for the slow networks, it was working okayish, like 1 megabit, maybe even 10 megabit per second. It was okayish. But when we got to the gigabit of networks, like in this case, 1 gigabit or 10 gigabit network, then picture became quite a bit bad. And bad in the sense that when we got in a congestion avoidance stage, we do our increase extremely slow. And to get to the maximum capacity of this 10 gigabit network, there's actually, you have to receive all the acknowledgement with a very high, all the acknowledgement that you send out. So effectively, you have to, you cannot have losses with a very high probability, or like in terms of probability, you can have a loss with probability of 0.00000. Okay, no, I cannot even count amount of zeros in this picture. For that purpose, what they try to do, they simply try to change the behavior of the congestion avoidance stage. So instead of doing increase by 1 MSS every RTT, they try to do some different logic. Just to give you very basic idea, kind of comparing HS-TCP versus conventional Reno. So with Reno, you would have a slow start, then drop to half, and very slow increase. Versus in HTCP, you would do slightly different. So you have a very rapid increase, the same slow start. Then you have a smaller decrease. It's still multiplicative, it's still kind of drastic decrease, but much smaller than half. So I think it's decreasing to 3/4 or something like that. I forgot the exact number. Then it do quite rapid increase. It's still linear increase, but with a different constant, so it's much rapidly. Then again, drop, increase, drop, increase, drop, increase. So compared to Reno, it's much more effective and much faster operating. For the CUBIC TCP, they do, the picture is slightly different. I didn't put the comparison with the Reno, but kind of you can imagine for the Reno it will be still congestion avoidance, drop to half and slow increase somewhere. In this case, for the CUBIC, what they're trying to do is to split, logically split congestion avoidance stage into the fast and slow increases. Fast, slow, and fast increase again. So like from the half to somewhere in the middle, it's kind of rapidly increasing over one side of the CUBIC function. Then around this kind of this middle part, it's a plateauing because that's behaviors of CUBIC function. And then when we pass the plateau, it's trying to increase rapidly. In fact, we're trying to discover more resources if some more resources available. So this one allows you to kind of have a drastic decrease, drastic increase, to some point increase, decrease, and like discover more resources if the resources available in the network. And CTCP is a kind of combination of several approaches. It has different zones, different stages. So there is some combination of HS-TCP, so it's still dropping, it's trying to increase faster at this point. But then if it passes some of the stages, it's trying to get back to the avoidance stage of very slow increase with time. And for the BBR, which is a new hot congestion control, they're trying to use delays for the purpose of estimation how fast fast you can do. So BBR is actually slightly different from all I'm talking today. Again, I already highlighted a few different congestion controls that were developed over the years. This is just a different picture of this timeline and a slight relationship of those congestion avoidance algorithms, just for the fun, because that's based on a paper that I wrote some number of years ago. But just to highlight, there's a lot of congestion control algorithms, specifically end-to-end congestion control algorithms. So what I'm not even showing on this picture is congestion controls that take in some input from the network, because sometimes you still can have input from the network if you control the network, like for the wireless cases, for example. So there is yet another bigger picture than this for those congestion avoidance algorithms. Okay, so I'll try to stop here. I think from this lecture, you should have a very solid knowledge of what congestion control is. So the congestion control, in simple terms, it's trying to avoid sending too much stuff to the network. And to do that, you need to do some form of estimation how much resources you have in the network. And to do that, you can rely on resources from the network itself. Unfortunately, we don't have that many of those resources available in today's networks. So an end host needs to do some form of estimation using losses, using kind of reception of duplicate acknowledgements. Sometimes it's using delays or some other mechanism, if you can imagine what it is, or some other magic. We have classic TCP approaches. Tahoe, that was the first one. Reno, it basically the classic approach. There are several modifications of Reno, like New Reno and HS-TCP, that basically, HS-TCP is being used in some of the operating systems, or at least you can enable that. There's a kind of currently used congestion controls, like CUBIC TCP is a default in a Linux operating system. I think some of them have been switching to BBR nowadays, but at least a couple of years back it was CUBIC TCP. And on Windows we use the compound TCP approach. Remember, we have the so-called fairness. So some flows not necessarily fair to each other, and depending on kind of, there is a fairness in terms of the algorithm actions. So this is what I was showing with the slow start and the congestion avoidance. But also remember, there's also fairness in terms of RTT. So this one is a little bit more complex and kind of harder to actually achieve that fairness. And one thing that you really have to pay attention is this fast recovery, because I most likely will be asking questions about that, is to speed up recovery from packet losses. So remember, you have a target window when you detected the loss using duplicate acknowledgement, but then you have to do this magical inflation of congestion window in order to keep the flow of packets going. Because if you don't, then you're basically going to be stuck waiting for the recovery to be finished in order to start sending more packets. Okay, again, I hope it was interesting, and see you in the next module.